Hello student, welcome back. Module 2, Lecture 1. Digital Image Processing, EC703A, Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Content: Digital Image Enhancement, Importance of Digital Image Enhancement, Enhancement in Spatial Domain, Enhancement, Frequency Domain. Digital Image Enhancement. Importance of digital image enhancement. Enhancement is the modification of an image to alter important portion on the viewer. Generally, enhancement distorts the original digital values. Therefore, enhancement is not done until the restoration process is completed. The exact meaning of this digital image enhancement is shown by these two figures. One is grayscale image, another is color image. In the grayscale image, this is the original image and these are the enhanced image of the original one. The original image is little bit of unclear, but it is, we can find this image or we can view the image, but it is not clear. Detail is not clear, like the backdrop. Whereas if it is enhanced by some techniques, the techniques will be discussed later, but now we are considering only the techniques. So the details of the back region also clear, here also clear. Here is again little bit of shabby picture is there. Original, but with respect to the original one, it is clear. So these are the different techniques of digital enhancement. So by enhancement, we can beautify image or we can see the details of an image by restoring the contrast of an image. Whereas in case of this color image, this is the underwater image. This is one of the very research hotspot now, underwater image processing. So this is the underwater image processing and it is enhanced version of this. Here one bluish layer is over there. So we have to remove this bluish layer. So by image enhancement, a complicated process of enhancement, you can see the detail of the fish over there, and even the very far end fish also you can find. There is also a lot of fishes are there swimming in the water. There are different in image enhancement technique both in spatial domain as well as frequency domain. First we are talking about spatial domain, means time domain, the domain, analogous domain where we are working. So in the image negative, the original image is in the scale of 0 to L-1. L is the number of maximum levels of intensity. So the image is transformed according to the image negative as S is equal to L-1 minus R. R is the original image intensity, S is the after this transformation, the transform intensity is equal to maximum level of intensity minus 1 minus R. So it is clearer, the image is just complement of its original intensity value. By this image it is clear, this is x-axis is the original intensity axis and y is the transform intensity axis, and this is the negative scale. And corresponding one picture is as shown as an example. This is a mammography of breast cancer. When it is taken the picture, it is not clearer how the image, how the tissues is affected by cancerous cell. But if we do the image negative of this, the image become clearer for the affected cells. So these are the affected cells. So it is quite clear by the picture. So then it is log transformation. S is equal to C log 1 minus R. R is the original intensity. S is the after transformation of log transformation, the transform intensity. So it is the original image of a Fourier transform image and it is its log transform image. So it is clearer after log transformation, the details of the Fourier, it is clear in the picture. Another is power law gamma transformation. S is equal to CR to the power gamma, where gamma is the different values and C is a constant. So depending on different gamma values, the output intensity pixels will be transformed. So C is a constant value, it may be 1. So if you do some practical software operation on image, it will be more clearer, because without handling the software, sometimes theoretical explanation is not sufficient. So I will always ask my student to do some practical operation as well as theoretical, because if you do practical operation at the same time of theoretical, it will be clearer. So in the x-axis in this figure, it is the intensity, input intensity, and y-axis is the output intensity. And according to the value of gamma, 25 to 0.4, different stretching will be there. And this is one example of this gamma transformation. It is a human spine, and when it is taken in the image, detailing is not clear. But if I do operation on power law or gamma transformation, image will be clearer, and depending on the value of C and gamma. When C is equal to 1 and gamma is equal to 0.6, this is the little bit of clearer image. When C is equal to 1 and gamma is equal to 0.4, it is the image. And when C is equal to 1 and gamma is equal to 0.3, it is the stretched image. Next, it is log transformation. Already we have discussed this one. Then it is frequency domain transformation or frequency domain understanding. So frequency domain filtering operation this is the fundamental equation. Already we have done in Fourier transformation operation. So FUV is the frequency domain pixel information of the original image or original pixel. After transformation, this is the after transformation, and then it is inverse transformation. The final intensity of the pixel will be like this. So H is the filter kernel or transfer function. So it is the original image, and after some transformation with the Fourier transformation with this kernel, we are getting this output image. So here the image, this image is darker, but this portion is clearer over there. So depending on my application, whether I want to make it darker or I have to make it brighter, according to the requirement, we can do this. And what is the advantage of frequency domain filtering? Already we have discussed that frequency domain filtering is very fast, as well as it is low computational complexity, whereas time domain filtering is high computational complexity and it requires much amount of time and space. Though frequency domain operation is more complicated, mathematics is requiring. Now enhancement in frequency domain also represented by this. This is the kernel of a low pass filter. These are the kernels of two high pass filter. Here the DC component is 0, whereas the DC component is A or some values are there. What does it mean? When it is low pass filter, the high frequency component cut out, and when high frequency components are cut out, detailing of the images are lost and image become blur. Whereas in high pass filtering, image becomes sharper, and when there is no DC component, image is darker. When there is a little bit of DC component, image become brighter. So according to my requirement, I can use this high pass filter, low pass filter with DC component or without DC component. So image smoothing. So image smoothing is nothing but in between image blurring and image sharpening. So too much of image blurring is very annoying to our eyes, as well as too much of image sharpening also annoying to our eyes. So there should be some optimization, that is image smoothing. So it is an ideal low pass filter. This is the kernel of low pass filter, ideal low pass filter kernel, and sharp cutoff is showing over there. So these are the center portion where the frequency can pass, and these are the outer portion where it will be blocked. This is Butterworth low pass filter. It is ideal low pass filter kernel, whereas Butterworth low pass filter kernel is roll off coefficients are there. Depending on the value of n 1, 2, 3, 4, how it will be used, we can use that. And this is the kernel of the Butterworth filter. So it is shown where depending on the value of n, how it is looking like. When n is equal to 1, it is very sharp spike. When n is equal to 2, this is n is equal to 5 and n is equal to 20. It is shown. So as the value of n is high, the filter become broader, so output will be blurred. Image enhancement in frequency domain using Gaussian filter, another important filter kernel. So it is showing the low pass filter kernel. So low pass filter kernel and the roll-off is showing is governing by this equation. D is equal to 0, 10, 20, 40, 100. So as the value of D lower, image will be sharper, and the higher value, image will be blurred. So this is image enhancement in the frequency domain. This is the ideal filter kernel, this is the Butterworth, and this is the Gaussian filter kernel. So this is references. Thank you. This is all of the day, and goodbye. We will meet soon.